Okay. Well, let us begin. Just a couple of quick reminders. Don't forget the quiz opened up today, and it'll be available for until 10 p.m. So I haven't checked on them, but if you've not done it, don't forget about it. Okay. Any questions right now so far? Hopefully things are going along pretty good for you. Um, but let me begin here with chapter 7. Chapter 7 is a little bit longer. We may take some time tomorrow also to finish it up, but it's a very, very important chapter. It deals with chemical bond or chemical bonding. Okay. Now, with respect to chemical bonds, of all the chemistry that's out there, there's really only two types of chemical bonds. Okay. One is called ionic bond. Okay. And that type of bond is very straightforward as far as how to identify it. It consists, like any compound, as we talked about a while back, consists of a interaction between two different elements. Okay. Well, for an ionic bond, it consists of an interaction between a metal and a non-metal. Ions. Now recall what ions are. Ions are nothing more than those elements that either have lost or gained electrons. So we talked about the metals, and we had a diagram or a periodic table that showed all the metals of the elements. Okay. All metals, just by their nature, want to lose electrons. And so by losing electron, either 1, 2, or 3, depends on how many valence electrons they have, they have a net charge of a positive. Okay. For example, just to refresh your memory, you got sodium. Sodium element, it's got 11 protons, which have a positive charge, and 11 electrons, which have a negative charge. Okay, so from a charge perspective, the 11 positives cancel out the 11 negatives, and therefore the net charge of any element, all 118, is 0. Now, when they lose an electron, for example, sodium has 1 valence electron. Now, how do we know that? To refresh your memory, well, we find it on the periodic table. Sodium is on group 1, 1A. That means it has 1 valence electron. And so of those 11 electrons that the element has, sodium, being a metal, will lose that 1 electron because the next energy level in now is full, and it has a noble gas configuration of neon. Excuse me, I had a senior moment there, had to look it up. Neon. And so now it has 11 protons and 10 electrons. So we got 11 positives and only 10 negatives. So mathematically, if we think about it, we have a net charge of a positive 1. Okay. So sodium comes into play with this sodium with this positive 1 charge. Okay, as an ion. And then we look at a partner, and we know it's a metal. So we look for a partner, which is a non-metal, and we're going to use the example of chlorine. Notice I said the name chlorine. IONIC tells you it's the element. Okay, we know by looking at the periodic table that chlorine has a total of 17 electrons. Of those 17 electrons, 7 of them are on the valence shell, the outermost shell. Okay, and chlorine is a nonmetal. And being a nonmetal, all nonmetals have a tendency to gain electrons. So in this case, chlorine, by gaining 1 electron, it fills up the octet. And now chlorine starts off with 17 protons, 17 electrons, okay? Net charge 0 for the element chlorine. The moment it picks up that electron, now it has 17 protons, 18 electrons, 17 positives, 18 negatives. We got one negative left over that does not cancel out because of the positives. So the chlorine now has a negative charge of 1, negative 1. And we change the name once the nonmetal becomes an ion, we change the name to chloride, IDE. We take off the INE for chlorine, which is the element, and add IDE, which is the ion. And so down the road, when you're looking at word problems, read them carefully. When they say, chloride, they're talking about the ion. When they say chlorine, we're talking about the element. Okay. So in this case, when they combine, you create what we all know as good old-fashioned table salt or sodium chloride. Okay. Now, sodium is a metal. Chlorine, in this case, chloride is a nonmetal. We create a ionic compound by definition. Okay. The thing to note about this is that the sodium has a full-fledged positive charge, and the chloride has a full-fledged negative charge. And we know that positives and negatives attract to each other. So in the solid form, they come together, they're attracted to each other, much like magnets coming together and attaching. They don't actually create a bond. And I use my fingers as an example to demonstrate a bond where they're sharing of anything. They come together by what is called electrostatic attraction, like two magnets coming together. Ionic compounds, for right now, when we put them in water, completely dissociate. That's one difference about an ionic compound versus the other type that we're going to talk about, is when we put an ionic compound in solution, they totally dissociate because they're not really sharing a bond and creating a true bond. Okay. Now, the other type, there's two names for them. One, you may hear the name molecular or covalent bond. Okay. They interchange the name covalent and molecular. Now, this is a combination of, at the minimum, two nonmetals. So two nonmetals combining with each other. And when that occurs, you have what's called a molecular bond. This is really a true bond because what's happening is electrons from one element and electrons of the other element combine to make a physical bond, a physical hookup between the two different elements. Okay, we're going to learn later on that that bond that they make could be either shared equally or not shared equally, which is related to the electronegativity that we talked about last chapter. Okay. All right, so a good example of this would be something like good old-fashioned H2O. Oh. H2O, I can't write subscript, so that 2 is a subscript. So water, hydrogen's a nonmetal, oxygen's a nonmetal. Okay, another one would be, let's say, carbon monoxide. We're familiar with that gas, poisonous gas. We got carbon and oxygen bond together. Okay, two nonmetals. There's an actual true bond between the two, and they're sharing those electrons together. Okay, so now one big difference about these molecular compounds, covalent bonds, and ionic bonds is that when we We put them in water, for example, they don't dissociate. A good example would be carbon dioxide, CO2. Okay, another good example, covalent bond. When you put carbon dioxide in water, or you put water in water, or carbon monoxide in water, they just dissolve. They don't actually break apart, okay, like the ionic compounds would. Okay, they remain intact as one species. Uh, Good example is your soda pop. Okay, carbon dioxide has got that fizz. All right, if you shake that bottle, all that carbon dioxide gets removed because it's not actually dissolved in there. It forms a little bit of solution, but um, carbon dioxide before is still carbon dioxide after it goes away from your soda pop. Okay, so all the chemical compounds that we have, there's only two types: ionic bonds and molecular bonds, or covalent bonds. Okay, and the thing to take away from this is to remember ionic bonds is a combination of two or more, any compound, but it's a combination of a metal and a non-metal. Okay, and molecular slash covalent bonds is a combination of a not of at least two different nonmetals. Okay, so that's the thing between compounds, the main point of this particular chapter. Okay, now download the shapes table. We're going to need this here for this particular chapter. Okay, so what do we know? We talked about chemical bonds. We talked about noble gases. We talked about the electron configuration. Noble gases are inert. They're very inert because the outermost shell is full. Okay, and the driving force in any chemical reaction is that octet rule, is by somehow have the valence shell full and be isoelectronic with a noble gas. So for metals, for example, metals, by losing electrons, they become isoelectronic with the noble gas behind them on the periodic table. Whereas nonmetals, when they become when they become ions, by gaining electrons, they become isoelectronic like the noble gas in front of it. Okay, so chlorine becomes isoelectronic with argon, and sodium, by losing that electron, becomes isoelectronic with neon, which is the metal behind it. Okay, driving force. Metals lose electrons, become cations. Nonmetals gain electrons, become anions. Okay, and so this ionic compounds, when we get a metal and non-metal, when that occurs, they form this charge. It's a full charge. Okay, and they are attracted to each other, and they come together because of the attraction. Now, for example, in this, you're asking here, what makes a good partner for calcium ion, or the +2? How do we know it's +2? Look at the periodic table. Find calcium. It's in group 2. It has 2 valence electrons. Point number 1. Point number 2, it's a metal, so it's going to lose those 2 valence electrons to give us a +2. And the question here is, what is the best partner? Okay, well, that would be, can only be an anion. It would not attract a cation because positives and positives don't attract with each other. So lithium ion would not be a good partner, but the bromide ion would be. Okay. All right. Other examples of ionic compounds: potassium chloride. We talked about sodium chloride, but you're at the point now where you can start making a lot of mix and match. You can take all the ions in group 1, with exception, and even hydrogen, but it's a different story for right now. Lithium, sodium, potassium, all of them, and combine them with any anion. So you already have access to a couple hundred different compounds: sodium chloride, potassium chloride, calcium chloride, or then talk about the bromide, and iodide, calcium iodide, calcium bromide. You see how you can put them all together, those are legitimate compounds. Okay. Now we're going to talk about down the road, like that one here, calcium bromide, why there's two bromides. But think about this for a moment. Okay. It's pretty self-explanatory when you think about it. We know that the bromide has a -1. Okay. And we know that calcium has a +2. Okay. Now, when we put ions together to make a compound, a formula, they have to come together such that all the negatives cancel out all the positives. So you can see the bromide has a -1, okay? But that calcium has a +2. So we need two bromides to cancel the +2. Hence, when we write the formula, we put a subscript 2 to tell us there's two bromides, okay? Notice with the chloride is a -1. Potassium is a +1. So it's a simple 1-to-1. Dog's barking, trying to get out. Give me 1 second. Let me. Sorry about that. All right. All right. Let's clear this up. Okay. Nonmetals and nonmetals that create covalent bonds. Also, the term molecular bonds. You'll see that also. Combination of two nonmetals. Okay. H2O, carbon dioxide, obviously all of the diatomic elements. Diatomic elements are kind of misleading. They're not compounds, okay? Because to form a compound, you have to have at least two different elements. The reason they're diatomic, and remember there's only 7 of them, have no fear of ice cold beverage. Remember that little rhyme? Okay. They do not exist, cannot exist, at least here on Earth, singly. So they actually combine with another same element. And hence we have H2N2, F2, Cl2, and so forth. Okay, so they're not compounds, just don't get the two mixed up. But they do form a covalent bond, okay? Because even though the compound by definition they're not different elements, they're the same element, but they form a special bond, a special type of covalent bonds. We'll have more to say about those down the road here. Okay. Now this is, I explained earlier why it's calcium bromide with two bromides, simply because we know that calcium has a +2 and the bromides have a -1. So we need to put 2 to balance out the calcium. Notice that we didn't put the 2 in front of the bromide, okay? We put the 2 as a subscript, all right? So that explains, this side explains that why we do that. And we're going to do a lot of this down the road of actually putting the ions together to write a formula. Okay. And so that's why it's important to identify the elements on the periodic table, because they're going to tell us from their position in the periodic table what their charge is, whether it's +1, +2, +3, whether it's -3, -2, or -1. Okay. And that information then allows us to put them together to write a formula in the proper number of each other. Okay. This slide here is asking you, which compounds are ionic? Okay. Well, by definition, any ionic compound is a combination of metal and non-metal. So let's analyze this. Okay. We have notice the names. Kind of keep track of the naming as a naming, because we have a whole chapter on naming compounds. But is pretty straightforward once you kind of you see the little trend here. Potassium is the front, is the metal. Okay. Bromine, which you would think bromine, but keep in mind it is bonded here with potassium. That's why it's written potassium, then followed by the bromine. Since it's not Br2 or bromine, it's by itself. Okay, so that tells you that is bromide, because now it's ionic form. Okay, so the name of this compound is potassium bromide. Recognize that potassium is a metal and bromide is a nonmetal. So that would be ionic. The next one here, SO3. Okay. Covalent this is a covalent compound. How do we know that? Because we got sulfur and oxygen bonded together. 90-some% of the time, the first element that you see written is a central atom. So in this case, sulfur is a central atom. And then what follows are the elements that are bonded around the central atom. And so in this case, sulfur is the central atom, and there's 3 oxygens. That the way it's written tells you that those 3 oxygens are bonded around sulfur. Okay. But in both cases, they are covalent. This is a covalent compound because in both cases, sulfur and oxygen, they're nonmetals. Okay. The name for that compound, SO3, is sulfur trioxide. Okay, we're going to get more in detail about naming these. Next one, HCl. This should be very familiar to you because all of us have that in our stomach. That is a formula for hydrochloric acid. Okay. Hydrogen, nonmetal. Chloride, nonmetal. Hence, covalent compound, not ionic. Br2, this is one of the diatomic elements, bromine. Okay. 2 nonmetals, not ionic. Notice here, next one down, carbon dioxide. Notice how we named this. We named sulfur and oxygen, and there's 3 oxygens, sulfur trioxide. Look it down with carbon dioxide. There's 2 oxygens, hence di. And then the last species, magnesium chloride. Okay, magnesium chloride, metal, nonmetal. Okay, so therefore, push the wrong button here. Hence, we have only 2 ionic compounds. Oh, give me another moment. I guess she's done. I gotta let her back in. All right. So of the list here, by analyzing each one, determine which is metal, which is non-metal. If there's a combination of a metal and a non-metal, we have quickly identify which ones are ionic. Okay. All right. And being ionic, if we were to put these in water, potassium bromide, magnesium chloride, it would completely dissociate, completely break apart. The others will not. Okay. There's one exception about the dissociation, and I'll have a lot more to say about this, though. Even though hydrochloric acid is covalent, it will dissociate. And we have a whole chapter on acids and bases, and hydrochloric acid is an example of an acid, the only covalent compound that actually dissociates, but all the other covalent compounds do not. This diagram here is demonstrating how taking the sodium ion and the in this case, the chlorine atom, let me restate that, the sodium atom or the element and the chlorine atom combining to form what we now know as sodium chloride, the salt. Now think about look at the diameter. The sodium atom is much bigger than the sodium ion. Now give this some thought. Remember we talked about the sodium atom a couple of slides back, and I said it had one valence electron out here. Specifically, it has it on the 3s1 energy level. Well, when it's the atom, the energy level is in the third period, okay? The third energy level, third shell. When it loses that electron now is gone. So then the valence shell now goes to the second energy level. So guess what? It got smaller. And that corresponds to the color there when it becomes an ion. This sodium atom, when it loses that electron, gets smaller in diameter because it lost that electron. The counter to that is the chlorine atom. It's in group 7. It's got room for one more electron. So it's going to pick up that electron that sodium gave up and put it in its valence shell now to fill it up. Now, by adding that one extra electron, that radius of the third energy level, the 3p5 that was started off, it now becomes 3p6. We added one more electron. The electrons repel from each other. So guess what? The radius of the ion becomes bigger, okay? And so the takeaway here is when you lose electrons, the radius of the ion is smaller. When you gain electrons from the nonmetals, for example, the radius of the ion is bigger, okay? Because the electron takes up more space. And this is the fascinating part here, is to me that at least, you got sodium element, which is very hazardous. It reacts with water violently, okay? And can cause explosions because it generates a lot of heat and hydrogen gas, which can ignite. Then we got chlorine, which normally is diatomic, but chlorine is a poisonous gas. Chlorine gas is very poisonous, okay? So here we got a hazardous metal, a poisonous gas. They come together, they exchange one tiny electron, and we create a whole new compound, an ionic compound called sodium chloride, what we can put in our French fries and not cause much of a hazard. And all that happened was one electron. It's like, comparatively speaking, is like losing one hair from your head and you become a totally different person. Yeah. Okay, so this is a solid. This diagram there shows you the ions of the sodium, purple color, and the green for the chlorides, and notice how in solid form they're very ordered. They come together with that electrostatic attraction. They're not creating a bond. They're just attracted to each other because they got a full positive and a full negative, like two magnets coming together. Okay, and there's some information about the size. All right, let me clear this up. Now, consider the magnesium and the sulfur atoms, and then consider the magnesium and the sulfur ions. Okay. The question is how many protons and electrons are in each of them, and then why would the ions bond together? Is the second question. So let's take a look at magnesium. Magnesium starts off with 12 protons and 12 electrons. Okay. It's in group 2. It will lose those 2 electrons. So now it has the magnesium ion has a +2 charge because it lost 2 electrons. So the net is a +2. Sulfur has a total of 16 protons and 16 electrons as an element. Okay, it is in group 6. And so therefore, being in group 6, it literally has room for 2 more electrons. Plus, it's a nonmetal, so it's going to gain 2 electrons. So now, notice the name here when I call this. I said the sulfur atom, when it becomes ion, the -2 ion, the name changes to sulfide, SULFIDE. Okay, so the sulfide ion now still has 16 protons, but it now has 18 electrons. So the net charge is -2. Okay, and so the ions are going to naturally come together to form the compound magnesium sulfide. Okay, magnesium, and they're going to come together in a 1-to-1. Why 1-to-1? Because magnesium has a +2 and the sulfide has a -2. So they just simply come together, just like the sodium chloride. Sodium had +1, chloride has -1. Simple 1-to-1. Okay. Now we talked about the compounds, but we talked about the ionic size, how when they're cations, by losing electrons, they get smaller. Okay, so because the orbits now where the electrons were are no longer, they're empty, so the radius gets smaller. The anions, compared to the corresponding element, get bigger because they gain electrons, and they added electrons into the valence shell, and those electrons repel each other, so they're going to force each other away from each other, and the radius gets bigger. Okay. All right. Question here: true or false regarding an ionic bond between aluminum and iodine? Okay. Question says the aluminum atom loses electrons and the iodine atom gains electrons. Well, how do you break that question down? Well, you ask yourself, aluminum, is it a metal? Yes. Being a metal is going to lose electrons. So that part of it is correct. Okay. The iodine, okay, is it a nonmetal? Yes, it is. Being a nonmetal, it will gain electrons. So that part of the question is correct. So be careful about these type of questions, because if it's broken up in 2 parts here, one part could be true and the other part could be false, or vice versa. If any part of that question is false, the whole thing is false. In this case, everything is true. So that is a true statement. Okay. Okay, this question is asking you, the aluminum atom is larger in radius than the aluminum ion. Okay. Well, to verify that, we know that aluminum will lose electrons. Okay. So by losing electron, the ion gets smaller. So yes, that is a true statement. The iodine atom is smaller in radius than the iodide ion. Notice the name change, iodine to iodide. Being the iodide, it gained electrons. Picking up an electron made the radius bigger. Hence, that is a true statement. Okay. And then the question here is the aluminum and the iodide ions form a bond by attraction, and that is correct. Specifically by electrostatic attraction, just similar to magnets coming together. Okay. The only thing we're going to say about metals, as far as bonding, pure metals on the surface, they just have a whole bunch of electrons. Okay. And they're just delocalized throughout the surface of the metal, and the electrons are shared by all the atoms. And that's why metals are very good conductors of electricity and heat, just because of the electrons on the surface of the metals. Very good conductors. Okay, now we get to covalent bonding, and that is a combination between two nonmetals. And when we do that, we get what are called shared electrons. We literally are creating a bond between two different elements, or the same elements, or two different nonmetals. Okay? You're going to have three types of bonds here. You can have a single bond, a double bond, and a triple bond. Now, the way we denote that, hopefully I can draw a straight line here, is instead of, to denote a single bond, you'll see a line written like that. Okay? That represents two electrons. And we can make two dots to represent a single bond, or we can just draw a line. Okay? A double bond would be just like an equal sign, but it's basically two single lines like that. You'll see that drawn often. Okay, each of those single lines have two electrons, so there are 4 electrons in a double bond. Okay, and then a triple bond, just like it stands, basically 3 lines like that, like that. Well, kind of, well, making me a little more even than I did, but 3 lines. Each represents 2 electrons that are being shared between the 2 elements, and there's a total of 6 electrons in that bond. Okay, and that's it. We don't have any more. When it comes to covalent bonds, we simply have a single, double, or triple bond. Okay, some good examples here are carbon dioxide, where there's a triple bond between the carbon is this central atom, and there's a triple bond between the oxygen and the carbons. Let me see if I can draw an example of that real quick. So one way you might see, you get the oxygen, the equal, carbon, the equal, and then the oxygen. Okay? That represents a 2 double bonds within the carbon. Okay, so if we count each line, we got 4 lines. Okay, and 4 lines, each one represents 2 electrons. So guess how many electrons we have around the carbon? 8. Okay, 8 electrons. Now you might say, well, what about the oxygens? Well, in the oxygens, we also have 8. But I'm going to try to attempt to draw a line here. They're not bonded, and we represent that as lines around the oxygen here. Remember, each line represents 2 electrons. Okay, so those yellow lines I drew around the oxygen, those represent 2 electrons that are not bonded. They're just sitting there on oxygen. Now, if we count the number of electrons around oxygen, the 2 yellow lines and a double bond, guess what? There's 8 around oxygen. Do the same for the other oxygen on the left-hand side. 2 yellow lines, that's 4 electrons, and then 2 of the blue color, the blue color lines, that's a total of 8 electrons. Guess what? All the elements in this formula we just drew have the octet fulfilled. The double bonds are being shared between the carbon and the oxygen on the right. And then the other double bond is being shared between the carbon and the oxygen on the left. The single lines are not being shared. They're solely on the oxygen. Okay. All right. And if we look at water, the same scenario occurs. We have a single bond between the hydrogen and the oxygen. And then around the red part here, we can draw 2 lines that represent electrons that are not being shared. So there's a if I can't draw it here, but in there, between the oxygen in the red and the hydrogen in the white, there's 1 pair of electrons on each side that are being shared. Okay. Now remember, hydrogen doesn't fulfill the octet. It has its own rule like helium. It's a duet. So there are two hydrogens around each hydrogen. So it's happy, if you will, to use that term. Around the oxygen, there's a total of 8. 2 of them are bonded and 2 of them are not bonded. But there's a total of 8. Okay? Hence the octet is fulfilled. So when we start writing covalent structures, covalent bonds, compounds, we have to keep in mind we need to fulfill the octet, with exception of hydrogen, which has a duet. Okay, keep that in mind when we move on down the octet. So we have single bonds, double bonds, triple bonds of electrons, like we just mentioned. Okay, now with respect to strength, single bonds are normally the longest bond, meaning between two elements. That bond is a little bit longer. And the weakest when we compare it to the triple bond. They tend to be shorter in bond length, but tend to be the strongest. An example of this would be acetylene torches. Acetylene torches, when you take acetylene gas, which has a triple bond, and you mix it up with oxygen and burn it, it is strong. There's a lot of energy given off. Enough energy to cut metal. Okay. And single bonds, we find a lot of that in your vehicle when you're burning gasoline. And they're not as strong as the triple bonds, but have a lot of energy in them. Okay. Now, when we put two elements together to create a bond, okay, each element comes with their own radius. We talked about the radius, okay? And in this example here, we have the hydrogen atom, which has a radius of 0.07 nm. Those units are called nanometers, NaNO. Okay, that's down in the atomic scale, pretty tiny. And then the chlorine atom has a radius of about 0.099 nanometers. When they combine to form hydrochloric acid, HCl, it was thought that the bond angle will just be simply the sum of the chlorine atom and the hydrogen atom. But what it is actually much less. Okay, the sum of the radius of the hydrogen and the chlorine atom is 0.136. But in reality, when measurements are done, the radius between the two, when it formed the compound, is 0.127, much less than 0.136. So what that tells us is that there is overlap, okay? And that's what we got in here, right in here, overlap. And since they're actually forming a bond, okay, and some of the electron density of the hydrogen is overlapping with the hydrogen electron density, I should say, of the chlorine, in this case chloride, to form a bond, and they're sharing that bond. Okay. All right. Now, these bonds have a lot of energy. Okay. And it takes energy to break it or to form a bond. Okay. When we're breaking bonds, it requires energy. Okay? Breaking bonds requires energy. Therefore, what that means is that energy is a reactant, and that energy is absorbed. All right. And therefore, it gets cold because it's what we call an endothermic reaction. A good example would be if you go to the pharmacy and you buy a cold pack. I don't know if you've ever done that, but they sell these cold packs. If you get the pack and you smack them, okay, the packet gets cold, so you can put them on like sore arms and so forth, twisted ankles and so forth, if you don't have ice cubes. Well, that's because there are breaking of bonds, chemical bonds in that molecule, in that compound, in that package, and requires energy to do that, and it takes it from the environment, resulting in the cold material. We call that endothermic. It's an endothermic process. Okay, and what we mean that heat or energy is a reactant. This is an example of a chemical reaction. We we have the arrow here. That arrow tells us when you see that there's a chemical reaction. What we have on the left side of the arrow are what we call reactants. Those are the things that are reacting to form what's on the right hand side of the arrow, the products. Okay, so this is an example of a chemical reaction. Reactants on the left side of the arrow, products on the right side of the arrow. And so what they're saying up there is for endothermic reaction, heat or energy is a reactant, and therefore on the left side of the arrow. Okay. Now, when we're forming bonds, it releases energy, and that is what we call exothermic. Energy is being released from the reaction. And so in this case, energy slash heat is produced and it's a product. Another example of this is something you may have used, say, in pharmacy. They got cold packs, but you know what? They also have hot packs. You can buy, smack them, they get warm. Okay, so you can use them to warm whatever, again, maybe a part of your body or something, where they want you to put a heat pad on it. Okay, that's a good example. So in this case, heat or energy is a product, and we put it on the right side of the arrow. Okay, so exothermic reactions give off heat, and heat or energy is a product. Endothermic reactions get cold. They require heat from the environment and hence get cold. And energy or heat is a reactant. Okay. Now the question here is true or false regarding this compound H2S. Okay. Question is, are electrons shared? Well, to answer this, you look at the elements. You have hydrogen and you have sulfur. Okay. That means you have two nonmetals. You have two nonmetals. That means you have a covalent compound or molecular compound. And if you have a covalent compound, then you have sharing of the bond. So yes, okay, this is a true statement. If any of those would have been a metal, which they do make sodium sulfide, then that would have been that comment would have been a false. Okay. Second question. The bond between hydrogen and sulfur is ionic. Okay. Well, it can't be. Why? Because we have two nonmetals. So that would be a false comment, false statement. And then, as I was saying here, the hydrogen bond is less than the sum of the two atomic radii. Remember that slide where we had hydrogen and I believe it was chloride atoms coming together? Okay. It turns out that that bond, after they formed the product, was much less because there's overlap of those electrons. Okay. So that this is a true statement. And then breaking the HS bond releases energy. It's a false statement. Breaking the bond requires energy. Okay. This is hydrogen sulfide, very nasty smelling gas. All right. Now, we got to talk a little bit about what are called Lewis dot structures. Sounds complicated, but it's not. Okay. All that is here is you write the symbol of the element, and then we put dots around the element that represent the number of valence electrons. That's it. Now, how do we know how many valence electrons? We use a periodic table, find its group. Okay, so hydrogen, for example, has only one valence electron. So we will write the symbol hydrogen and a dot. Okay. All right. So now, why do we want to know this? Because we're going to start putting molecules together. And I said way back when, all the action in chemistry occurs with the valence electrons. So we need to know when we put them together to make a compound, how many valence electrons each atom has. So we can actually start writing and putting formulas together. Okay. So to do the Lewis dot structure of the simple atoms, here's the example. Potassium only has one valence electron. It's in group 1. So everybody in group 1A, that would be the Lewis dot structure. Okay. Oxygen's in group 6. Okay. And so it would have 7 electrons, 7 dots around it. And that would be, so everybody in group 6 would have that. I keep saying 7. Group 6. Silicon's in group 4. Okay. So you put 4 dots around it. Now you want to not put 2 together right away, but you go around the atom. So start up on top if you like and put 1 dot. If it just needs a second dot, go to the next, to the right side, hit a second dot. Okay. And so keep them separated because you're filling them up just like we do the, for example, let me do this. See if I can, let me clear this for a second. All right, so let's do silicon. So we look up silicon, we know got 4 valence electrons, so we put 1 dot there. And then we go around, put the other one there. We keep going around and until we got 4. So I've highlighted the 4. If I have 5, then I can start doubling up, just like oxygen was. Go start doubling up, but I'm eventually going to end up, in the case of oxygen, with 2 electrons or 2 dots there by themselves. All right. So here's iodine. Everybody in group 7 would look like that. 7 valence electrons. All right. So by knowing how many valence electrons now, we can actually start writing structures. There's Lewis dot structures for the atoms, but we're going to start writing Lewis dot structures for compounds. Okay. And what we do is we add up all of the valence electrons that are in that compound. Okay. And you'll be given the formula. Okay. And you'll also be told which is the central atom, which means that the central atom will be in the middle, and whatever is bonded around it will simply go around the central atom. And normally the central atom will have an underline or underscore, or will be put in bold, or you'll be told the so-and-so atom is the central atom. Okay. And then once we identify the central atom, then we can place all the other atoms around the central atom and draw single bonds around them. Okay. So we got to recall the octet rule. Okay. Because everybody, once we start writing formulas, have to fulfill the octet rule. Except hydrogen. Hydrogen just needs 2 electrons around it. Okay. Everybody else needs 8. And those 8 can, like I was trying to explain earlier with water, some of them are shared by actually forming a bond. They're shared between two atoms, and others may be not shared. They could be on this on an atom, just sitting there. They're not bonded to anything, not being shared. Okay. So when we talk about bonded, we call that bonding pair. They are shared with each other with another element. If they're just sitting there on an atom doing nothing, they're not bonded. Those are called lone pair. Okay. Now, once we write down, the thing about this is once we know how many valence electrons we have, that's the number we have to work with. We can't arbitrarily just add more electrons or take electrons away. If we have 8 valence electrons, then we got to work with 8 valence electrons. Okay. Now, once we put all these together and we see that one atom is not fulfilling the octet rule, we start creating double bonds. And if that still doesn't work, then we create triple bonds. We're not creating them, we're taking these pairs that are now bonded and having them share with the other atom. Okay. So let's see if we can try a couple. Let's do water, for example, H2O. Well, first thing we got to do is we got to add up all of the valence electrons that each element brings to the table. Okay. So I'm gonna finish this slide and we'll continue in this spot tomorrow. But hydrogen has 1 valence electron, but there's 2 hydrogens, so it's 2 times 1. Okay. Oxygen is in group 6, so it has 6 valence electrons. So in total, we have 8 valence electrons to work with. Oxygen is a central atom, and unfortunately didn't draw it here, but you will see either underline. Okay, so we have oxygen as central atom. So what I can do is I can draw oxygen. Okay, and I can make a bond because I have 2 hydrogens. Okay, I can quick. That's supposed to be hydrogen. Since I have 8 hydrogen, 8 valence electrons, take that 8. You're always going to have an even number divisible, a number divisible by 2. So 8 divided by 2 is 4. So I have 4 pair to work with. Okay. And having 4 pair, and by drawing the formula very quickly here, like I did on the right hand side, I took care of 2 pair. Okay. Already, because the 2 pair are bonded with the hydrogen. So that leaves only with 2 pair. So I have to put them someplace. I can't put them on the hydrogen because the duet for hydrogen is fulfilled. So they must go, and let me change the color a little bit. Those other 2 must go up. You got oxygen, hydrogen, hydrogen. Oh my goodness. Bear with me. It's tough trying to use a mouse here to draw something. Okay. And so let me change the color. And so the other 2 pair I have to put on the oxygen. So total, I still have 8 valence electrons. Each line represents 2 electrons. So I got 2, 4, 6, 8 around the oxygen. And the hydrogen has 2 around it. The ones in red are shared. They're shared by both the hydrogen and the oxygen. So I can count them toward either one. I can count them toward the oxygen and then or count them toward the hydrogen. Okay. So here the octet is fulfilled for everybody and the duet for hydrogen. Okay. And so I thought I had the structure there. Let me clear that out. Yeah, much better. So I can see here that I have uh, two, one there and one there. Those are a bonded pair, okay? And then I have two that are lone pair, one there and one there. Keep in mind, I can draw the line. That line represents two electrons. So if I count the number of electrons around oxygen, I have total of 8. Two bonded, two lone pairs, I should say. So that's a total of 8. And around the hydrogen, it's a duet rule. It doesn't have the octet, okay? Because it only has one electron to work to begin with, okay? So it's happy. So this formula is the Lewis dot structure for water, okay? All right, so let me stop it here.